Okay, so the organizers asked me to talk to you today about observing modes available for cycle 1. So I'm actually going to try and do 3 things for you. One is I'm going to try to give you some insight into the different modes available for JWST on the different instruments, and to try to compare and contrast them, and to point out certain things about some of the modes that you might not appreciate, but could be important for planning. In the course of this, I think later on today we have both a JDocs talk and some JDocs homework. So if you pay really close attention to some of the observing mode aspects, the answers for some of the questions are actually in my talk. The second part is that Jeff already did a really nice job going through the GEO Cycle 1 call for proposals. So I'm going to reiterate and maybe give you a little bit more detail on some of these aspects. And then finally, one of the things that you'll be learning about while you're at this workshop is some of the observing planning tools. So for example, the exposure time calculator and the astronomer's proposal tool. The version of the APT that you'll use while you're at this workshop this week is version 25.2. But the version that you will submit your proposals with is version 25.4. That version will be released November 20th, and there will be additional observatory capabilities that will be included in the updated release of APT, and that's meant to prepare everyone to submit their Cycle 1 proposals. So if you were to try to construct your proposal today, you may find that there are some capabilities in there that don't exist but will be available during Cycle 1. So I don't have enough time to give you the extensive list of all of those things, but I'll try to highlight a couple or a few of them that I think are of particular interest. Okay, so I'm just going to dive in and start talking about the different instruments. The primary near-infrared imaging instrument is the near-infrared camera, NERCCAM. NERCCAM really is a camera in the sense that we think of our digital cameras, for example. It actually is 2 redundant instruments that are bolted together, Module A and Module B. And it has a short wavelength and a long wavelength channel. And there's a dichroic that splits the light from the instrument into the short wavelength and long wavelength pieces, so you can image simultaneously in the short wavelength and long wavelength channels. I say that it's really a camera in the sense if you look at the number of pixels that are associated with the short wavelength channel, it's actually like a 32 megapixel, thank you, camera. So it's really comparable to the digital cameras that you buy and take pictures with today. The long wavelength channel has fewer pixels. It's more like an 8 megapixel camera, but still they're approximately Nyquist sampled. So the short wavelength channel goes between about 0.6 microns to about 2.4 microns. It's critically sampled at 2. The long wavelength channel goes from 2.5 to 5 and is critically sampled at 4. So we expect, of course, NERCCAM to be the prime science imager at 0.6 to 5 microns. And we expect it to be popular for parallel imaging. NERCCAM actually has 2 wheels in it. It has a filter wheel and a dichroic wheel. And so not only is there the possibility for direct imaging in the traditional sense, but there are also grisms in the dichroic wheel. And so you can obtain wide field slitless spectroscopy. This is actually the prime instrument for wide field slitless spectroscopy at 2.4 to 5 microns. It has a moderate resolution of about 1500. And this will be, I think, particularly interesting for measuring kinematics and deblending lines for example, high Z galaxies. And this is in contrast to the near-infrared slitless spectrograph, imager and slitless spectrograph, NIRIS, which operates at shorter wavelengths, which I'll show a similar slide for later. NERCCAM also has a coronagraph on it. It is the prime chronographic imager at 1.8 to 5 microns. It has 2 kinds of Colting masks, spots that come in 3 sizes. The radius of the spot that you select depends on the wavelength that you're observing at. And then it also has wedges as well. The spots are a little bit oversized in the sense that the inner working angle is about 6 lambda over d. The inner working angle for the wedge is is a little smaller. It's about 4 lambda over d. And then there's also a couple of time series observations modes for NERCCAM. One is imaging, so it's the prime TSO imager at 0.6 to 5 microns. And then just like you have the wide field slitless spectroscopy mode, there is a GRISM time series mode, which is a mode using the GRISMs, which is optimized for TSO observations. So we expect this to be popular for GRISM observations at 2.4 to 5 microns. And the nice thing about it is because NERCCAM has the short wavelength and long wavelength channels, it gives you simultaneous short wavelength imaging as when you take your long wavelength spectra. So one of the things that I think is important to appreciate about NERCCAM is because it has all of those pixels, it can generate a lot of data. And there are constraints on the amount of data that can be returned from the observatory. So this is set by the storage capacity of the data recorder and the maximum downlink. So the great thing about APT is that it will calculate the length of your observation, and it will know approximately how much data that you will take. And so if you exceed the capacity of the solid state recorder, it'll actually give you a warning. And so this is just a little shot of a screen capture of if you were trying to plan one of these observations and you exceeded the data recorder, what would happen? You would get all these little red X's associated with the visits that have problems, and it would actually throw you this error saying that you've exceeded the allowable rate. You can imagine that there are proposals that don't strictly violate this upper limit, but have a relatively high data rate. And we encourage you in those particular cases to submit your proposal, and because they may be allowable, but after acceptance, they may need to be modified in order to comply with the data volume and data rate limits. So one of the ways that we try to get around these data volume problems is by averaging frames together into groups. So this is a common strategy that's adopted by all of the instruments. And what I'm showing you in particular are the readout patterns from NERCCAM, since NERCCAM is the instrument that has the potential to generate too much data. And so you can imagine that if you could, the kind of data you would always want to take is in rapid mode. And in this particular case, you would return every frame that was read out by the detector. So remember, these are non-destructive read detectors. You can save each frame. And then the onboard electronics allow you to average frames together into groups. You can average 2, 4, or 8 frames into a group. And then in addition to try to push out for longer exposure times or integration times, we also offer the possibility of not just averaging frames together, but also skipping frames as well. So you can see this is the whole variety of readout patterns that are offered by NERCCAM. The other instruments typically only have a couple of readout patterns, so they're much more straightforward. So I just wanted to let you know that there is some general guidance offered for how to select readout patterns, particularly for NERCCAM. And I provided a URL down here that shows you, I should remove this stage because that's, I'll fix the slides. But you can get to this particular JDocs article, and it gives you advice for how you can select the appropriate readout pattern depending on your total exposure time and the signal to noise ratio that you hope to achieve. And so we have here some just general generic advice for how to select the readout pattern that you want. So you always want to go for the most number of groups for the integration time that you need and the largest number of average frames per group. So, but of course, so this tells you that you get the most sampling possible and you return the most data possible. But this, of course, has to be consistent with both the saturation and data volume limits for the instrument. So I wanted to point out a couple of Mosaic considerations for cycle 1. So for mosaics, particularly large mosaics, there will be some issues in trying to fully plan your mosaic within the APT. So proposers are instead required to submit a complete APT file of programs requesting mosaics. And so the difficulty is that at this time, the guide star catalog may be insufficient to find guide stars for all of the mosaic tiles at a single time. So if this happens, the recommendation is that you split your mosaic into two parts. So this is called tile splitting, and that you should try to group together or find a position angle for which you can observe the largest number of tiles at a single time, because that fixes the position angle of the observatory and imposes a scheduling constraint on the long-range plan. So it's really important for ST to understand what scheduling constraints you have, and know that ST may have to adjust the position angle to minimize disruptions to the schedule. And then, of course, you want to take the tile that is more challenging to schedule because of problematic guide stars or something like that for a different position angle from the majority of the mosaic. I wanted to highlight an upcoming feature in APT 25.4 for Nercam. This is the addition of several new dither patterns. So this is the Nercam field of view here. And so you can see module A, module B, and the 4 detectors that make up the short wavelength channel and the big field of view for the long wavelength channel. You can see that there is a module gap between the, a module gap between the A side and the B side. And so you can imagine wanting to dither to close that gap. There's also these chip gaps between the SCAs and the short wavelength channel. Again, you can imagine wanting to dither to cover an area better. So there were pre-existing dither patterns to achieve those kinds of goals, but as we've been learning more about observatory operations, the team has designed a new set of dither patterns that better optimize the offsets, and so essentially try to make the observations more efficient. Okay, moving on to NIRIS, the near-infrared imager and slitless spectrometer. So it has 4 modes, wide field slitless spectroscopy. It's the prime instrument now at 0.8 to 2.2 microns. It has a significantly lower spectral resolution than NERCCAM, and we expect this to be popular as a parallel mode. So this is wide field. In contrast, we also have single object slitless spectroscopy offered. So this uses a large grism, which distributes the light spatially in direction orthogonal to the spectral dispersion, so that you can look at very bright targets. Indeed, this mode was optimized for TSO observations, time series observations of transiting exoplanet host stars. It operates at 0.6 to 2.8 microns, has a medium resolution of about 700. NIRIS has the only aperture mask interferometer on board. It's the highest spatial resolution imaging available on JWST, operates at slightly longer wavelengths, 2.8 to 4.8 microns, and has an approximate contrast performance of 10 to 4 for separations of 70 to 400 milliarc seconds. And then finally, NIRIS, because it has the backup filters for NERCAM, also provides imaging. It's mostly the secondary science imager. You can't operate it as the prime science imager. So this is to augment, for example, if you're doing NERCAM imaging and you'd like a larger field of view. So one of the features that I wanted to highlight, again, upcoming in APT version 25.4, is a change to some of the TSO modes. So I highlighted a couple of the TSO modes for NERCAM and one of the modes for NIRIS already. The way that TSO modes are distinguished from the regular observing modes is they all include target acquisition, they don't dither, there's no selection of the dispersion direction. And so the new upcoming capability is to allow very long exposures. So this is greater than 10,000 seconds or up to 50 hours. Next is the near-infrared spectrograph, NERSpec. It has 4 modes. The multi-object spectroscopy mode, which has already been alluded to. So it provides a spectra of up to 190 objects in a 3 arc minute by 3 arc minute field of view, using tiny configurable shutters with a MSA. It also has an image slicer, so an integral field unit, which provides 3D imaging spectroscopy of a 3 arcsecond by 3 arcsecond field of view, corresponding to spaxels that are about 0.1 arcsecond. There's also a fixed slit, which provides high contrast single object spectroscopy. This uses slits that are cut into the metal MSA support structure. And finally, there's the bright object time series. So this is the TSO mode for NERCCAM. So it essentially uses the largest aperture fixed slit, which is 1.6 arcseconds. And again, this is optimized for high precision spectrophotometry of bright targets. So I just wanted to give you a little bit of information about the MOS mode on NERCCAM. So this shows you the MSA. So essentially you can see all of the slits here, and then in the middle, this is where the fixed slits are cut into the MSA support structure, and you can see the size scale here. So I said previously that MOS observations can accommodate about 190 targets at an R of 100 and about 55 targets at an R of 1,000 and 2,700. So I think it's important to highlight that in order to use the MOS mode as efficiently as possible, it's useful to have very large input catalogs with source densities on the order of 720 per square arc minute and 240 per square arc minute. Again, just to maximize, to ensure that you have enough sources to disperse in every row of the MSA. I just wanted to make a couple special comments about MOS observing planning for geocycle 1 and beyond. One is that unlike imaging, it's not you're not required or not asked to specify the exact orient and MSA configuration in the proposal. You can specify a preferred orient within a range of a plus or minus 15 degrees. You are asked to include a target catalog covering an area with a radius of at least 3 arc minutes for any particular pointing. And again, it's important to oversize the catalog to maximize MOS multiplexing. Approved proposals do not have exclusive access to a field, thus the full list of targets cannot be reserved. However, some high priority targets may be flagged. There's no guarantee that any one target will be observed. Proposals may be submitted with source catalogs that overlapped with previously accepted proposals. Proposals must identify duplications. Previously accepted proposals will have priority in target selection, as Jeff already discussed. So multiple proposals using overlapping source catalogs may be proposed and accepted by the TAC during the same cycle. And in such cases, the TAC will provide a clear specification of the relative priority of these proposals. I just wanted to give you a little note about the astrometric requirements for target acquisition, specifically for MOS observations. If you would like to obtain MOS observations with data that's well flux calibrated, then it's important that your targets fall within the shutter, near the center of the shutter. There's a nice documentation showing you the throughput as a function of shutter position. But the general rule of thumb is you would like 5 to 10 milliarcsecond astrometric accuracy of the target. And so this requires HST, ACS, or WFC3 pre-imaging to understand the positions of the targets well enough, or JWST NERCCAM observations. Which brings me to my next slide, which is during cycle 1, it will be possible to propose follow-up observations of JWST pre-imaging. So in these particular cases, your prime science interest is probably spectroscopy of targets, but you don't have sufficient astrometry to configure the MOS. And so you can ask for this same cycle follow-up spectroscopic observations of sources identified through JWST imaging programs. So there was actually an example science use case of this presented at the May JWST PPS workshop. And this was a NERCCAM MOS observation of IC348, brown dwarfs, and they were identified, or they will be identified via NERCAM pre-imaging. So this is from a NERCCAM GTO program. But if you are interested in NERCAM pre-imaging, I encourage you to check out this particular science use case. So I wanted to mention the upcoming features in version 25.4 for NERCCAM Target Acquisition. So these are the currently available target acquisition possibilities for NERCCAM. They all currently, these two currently involve usage of the MSA, and the bright object TA requires the 1.6 arcsecond, the wide aperture, the large slit. So what happens in standard target acquisition right now is that all of the shutters in the MSA are opened, and you try to centroid on somewhere between 5 and 20 targets to understand what the pointing of the telescope is. And you actually make this observation 2 times, once and then a second time with a half shutter offset in both directions. This is a little bit time consuming because you can imagine you have to centroid on a lot of targets. So there's also a verify only option that just acquires the image so you can reconstruct the pointing afterwards. And then this is in contrast to the broad object TA, which is currently only implemented for the time series mode for bots for NERCCAM. So the upcoming TA capability is really an expansion of the bright object TA that was implemented for bots. So now it'll be possible to look at a bright reference object using either any of the fixed slits or the IFU to determine the spacecraft pointing. And then a new option will also be no target acquisition. Moving on to MIRI, the mid-infrared instrument. MIRI has 4 modes: imaging, coronagraphic imaging, the low-resolution spectrometer, the medium-resolution spectrometer. For imaging, it is the prime science imager at, oops, this is a typo, this should be 5 microns to 25 microns, and we expect it to be popular for parallel imaging. It is also the prime coronagraphic imager at 10.65 to 23 microns. It achieves this using 1 LEO, which operates at 23 microns, and 3 4-quadrant phase masks that operate at 10.65, 11.4, and 15.5 microns. The low-resolution spectrometer offers an R of about 100. We expect this to be the prime spectrometer for observations of faint targets at 5 to 12 microns. This is because it has a substantially higher throughput than the MRS. Its throughput is about 50%. It also includes a slitless mode for a high-precision spectrophotometry. So this is MIRI's TSO mode. The medium resolution spectrograph is an IFU. It's actually 4 IFUs that have concentric fields of view. It's the prime spectrometer at 5 to 30 microns for this resolution of 3000. And it's not recommended for high precision spectrophotometry in cycle 1. So a couple quick things I wanted to point out for MIRI. One is that unfortunately, JWST does not operate as cold as Spitzer. And so if you try to extrapolate based on your Spitzer intuition for how MIRI will perform, you'll actually be a little bit off. So this plot here shows you what the background looks like in megajansky's per steradian as a function of wavelength. And you can see here, for example, this is the scattered zodiacal light. And then as you come up beyond 3.5 microns, this is thermal emission for the zodiacal light. This is galactic emission, both diffuse and from other sources in our galaxy. And then you can also see that there's a red curve here as well, and it's particularly important for wavelengths longer than about 15 microns. This is actually telescope thermal emission. So because JWST operates at 40 Kelvin, it produces the dominant background source at wavelengths longer than 15 microns. And so it's actually so bright that it's hard to operate MIRI in imaging mode using the wide 25 micron filter because it's if you try to read it out in full frame, essentially you'll saturate the detector. And so when the MIRI operations were being outlined, this is one of the reasons for some of the subarrays that have been provided. There's one that's called the Bright Sky, which is a 512 by 512 subarray. And this should help to minimize the amount of background from the telescope thermal emission. Another thing I wanted to point out for you about MIRI is with the MRS, their MRS has a relatively small field of view, and it's possible within the MRS template to obtain simultaneous MIRI imaging. So this is important for a couple reasons. One is you can imagine it's efficient to get science imaging observations at the same time as you obtain your spectra. But another consideration is that you may want to mosaic a field of IFU pointings together. And so by observing simultaneously with the imager, you can better reconstruct the pointing of the telescope by making astrometric measurements of stars in the field. Let's see. And then I just have a couple of slides and then I'm done. So the last two things that I wanted to mention, one is parallel observations. So Jeff already alluded to this. So there's two kinds of parallel observations. One is called coordinated, and this is when an observer writing a proposal specifies the use of more than one instrument at a time. So if you know, for example, that you want to make you're mapping the sky and you want to map both with NERCCAM and MIRI at the same time, that would be considered a coordinated parallel observation. We anticipate being able to offer 5 different kinds of coordinated parallel observations. In addition to coordinated parallel observations, there's the possibility for what are called pure parallel observations. And in this particular case, a separate PI has specified the prime observation, and you can specify how a second instrument can be turned on and used at the same time. So this, for example, might piggyback off of the prime observations pointing to be able to make scientifically useful observations. So the one thing I want to point out is for direct imaging, you will not necessarily be able to use all of the filters that NERCCAM and MIRI have. You'll be able to use the standard narrow, medium, or broadband filters. And then I just have this, I think this is the last slide on survey proposals, which I think Jeff already sort of described. Just to quickly reiterate, so the Operations Center has a long-range plan with a duration of about 1.25 years. There may be gaps based on the RA distribution of approved targets. So to increase observing efficiency, short wavelengths drawn from from these survey programs can be used to fill the gaps. So there'll be allocated time to cover observations of a specific number of targets drawn from a larger sample. And just like with the MOS observations of any particular target cannot be guaranteed. They ask that you select targets over a large range of right ascension, more than 12 hours, and that individual observations are limited to 30 minutes of science integration. And so these can be small, medium, large treasury calibration. The last thing I wanted to highlight, is just the schedule for APT development. So here we are today, the APT 25.4 with the version of APT that you can use to submit your proposal will be available November 20th. This is 10 days before the GEO Cycle 1 call for proposals is released that Jeff discussed, and in advance of the due date for the proposals, which is March 2nd. And then, of course, for more information, please see the JWST documentation. And this is where the call for proposals will live once it's been released. Thanks for your attention.